Assalamu alaikum. In earlier sessions, we've seen that scientific data is statistical in nature. That is, data generated from scientific investigation often has a spread of values, which is in contrast to deterministic models in which you would have an exact result. But in scientific studies, we have probabilistic results, which mean that inherently there is going to be some random variation in our data. In other words, our data is going to have some spread. Today's session is going to talk of techniques and of different ideal distributions which people have come up to describe this dispersion or spread of data. So we start by, first of all, identifying that empirically data can take, any distribution. What we are interested in is finding some common distributions that occur a lot of times. So then we can match the empirical data that we have with some of these distributions and try to see and imagine what actual distribution created the data that we have. So in light of this remark, let's start this session. I'm going to first of all talk of how are distributions distinguished, and then I'm going to talk of one particular kind of distributions in which you have randomness, but that randomness is mild in nature. It is not very drastic. Most of your values would be close to your typical value. In a future session, we'll be seeing that all randomness is not like that. In fact, the kind of randomness which is most pertinent to network performance evaluation study is a kind of a wild randomness in which particular measurements can actually take values which are very far away from the typical value. So let's start initially by talking of how are distributions distinguished. So we've earlier mentioned some of the aspects of distinguishing distributions when we talked of summarizing data. So let's just recap some of the things we've covered. We've covered that a data distribution or the data that we have may have a spread which is symmetric. In that case, most of your values would be centered around a central value, and the values would be symmetric around both sides of the center. You may also have a skewed distribution in which the chances of having data on either side of the central value is not the same. In fact, data is more probable to occur on one side. So this would be a skewed distribution. So let's recap what we did. On the slide now you can see samples of symmetric distributions. So symmetric distributions can be mound-shaped like the one in the center that we have, and the typical bell-shaped curve is in this form. So it can also be symmetric but not follow the bell-shaped curve. However, it's very common that we have the bell-shaped curve that we associate with the normal distribution. So in other cases, we can actually have distributions that are skewed. And you can see such distributions now. You can see a distribution in which the tail of the distribution is leaning towards the left side. You would call this a left skewed distribution. So remember, the distinction that we make is based on the tail. So left skewed means that the tail is skewed towards the left hand side. We would also call this a negatively skewed distribution. You can also have a right skewed distribution in which the tail is towards the right hand side. And in fact, this is more common in network performance evaluation studies, because on the left hand side, most of the values are bound by zero value. You cannot have, for example, negative times. You cannot have negative counts. So in such cases, most of the distribution that we'd be interested in would be bounded on the lower side by the value of 0, and they would be skewed on the right hand side. Such a right skewed distribution is known as a positive skewed distribution. We also talked of the tails of a distribution, which means how atypical would we expect an extreme value to be. So while we've mentioned that in commonly in a distribution, most of the data values would be close to the central values. However, you would have some values which are distant from the typical central value. So we can classify distributions according to how extreme the values can take. So in case where the chances of having extreme values is negligible, we would call such a distribution as a light tail distribution. And in other cases, we can talk of a distribution in which the chances of having an extreme value which is very far from the mean is non-negligible. Such a distribution is known as a heavy tail distribution. Heavy in the sense that the chances of having a value which is very far from the mean is not small. So even in heavy tailed distributions, we can think of a symmetric heavy tail distribution and a skewed heavy tail distribution. In practical terms, we are usually concerned with skewed heavy tail distributions. We have an example of a symmetric heavy tail distribution of the Cauchy distribution, which we've talked of earlier in the summarizing data lecture. However, it's only of academic interest, and we usually do not find such a distribution in our practical studies. However, it is very common to find skewed distributions that are heavy-tailed. And in fact, we would be seeing in a future session when we talk of internet measurements and of fractal nature of network traffic, that in fact this is very important that we study heavy-tailed traffic, because most of the network traffic can only be modeled by a heavy-tailed distribution. So we'd be talking about this in due time. Furthermore, we can talk of two different worlds of randomness. So in one world of randomness, you have mild randomness, in which you do have variation, but that variation is predictable. It is also not very extreme. And this is the kind of random world that we are taught to study, that we study in usual statistic courses. And up till now in this course as well, we've talked mostly of the world in which the randomness is not very wild. It is relatively mild. We would call such a world as Mediocristan, following the term coined by Nassim Nicholas Taleb, who is a very famous author who has written a lot about extreme occurrences and the chance of randomness. His area of interest is mainly in studying randomness for the financial world. However, many of the ideas that he elucidates is actually very relevant to network traffic study and network performance evaluation studies. So such a world is known as Mediocristan, and in such a world, most of the values would be very close to the typical value. So to illustrate this, let's take an example. Imagine taking 50 of your friends to a hall and you measure the heights of all 50 of your friends. So you would come up with an average value. It is going to be very rare for someone to be very far away from the mean in such a setting. So it would be very rare for someone to be twice as tall as the average height. Much rarer to have someone 10 times as the average height. So imagine, even if we estimate the height on the lower side to be 5 foot, it is going to be very rare to find someone who is 50 feet tall. So such a world would be called a world of mild randomness. Most of the values would be close to the central value, and you would not have an extreme value which is, say, 100 times more the central value or 1,000 times more the central value. So such a world is typical of Mediocristan, or the world of mild randomness. Let's now take another example. In the same hall where you have 50 of your friends, imagine that Bill Gates, the world's richest man, now walks in. And now the measurement that you want to do is the amount of wealth these people have. Imagine you took this measurement before Bill Gates came into the room and you came up with some value. And then Bill Gates comes inside the room and you would see that the average wealth would increase by a lot. And this is despite the fact that you already had 50 people in the room. And this is typical of the world of wild randomness or the world of extremistan. In such a world, you can have an outlier which is so far away from the mean that it is going to disrupt all your usual statistics, which depends on finite variances of population. In such a case, and we would study when we talk of extremistan, there are distributions which in fact do not have finite variances, and those are practically seen. In such a case that we've seen in the example that we've just covered, Bill Gates' wealth is probably 100,000 or even 10,000 times the average that you computed before Bill Gates walked into this room. So what this means in practical terms is that the arrival of Bill Gates is going to change the mean by a large value. In other words, your mean is not going to remain robust. It is going to move around widely. And this is the case in extremistan. And when we get to cover distributions from this world, we would see the problems that we have in analyzing such distributions. So let's now talk about parameters of distributions. We've earlier seen that distributions are usually family of distributions, that you have a whole family of distributions that are very similar and they are actually tuned by some parameter. For example, in a normal distribution, you have two parameters, the mean value mu and the standard deviation, which is sigma. And depending on the parameter that you define, your normal distribution is going to look different. Similarly, for most other distributions, they are also parameterized, which means that their shape and their spread is actually dependent on one or two parameters. And we'll be covering them now. The first parameter of interest is the shape parameter. Let's call this parameter as alpha. In some distributions, you have a shape parameter, and depending on the value that you specify for this parameter, the shape of the distribution is going to change. So remember that not all distributions have shape parameters, but when they do, choosing an appropriate value would give you the shape of the distribution that you want. In other cases, when you have data and you want to match against a distribution, you can choose the parameter value of the distribution such that it fits the data that you have. Another parameter that we can talk about is the scale parameter, which tells us how spread the distribution is. In other words, how far away is the tail when it actually decays. So in many distributions, you have a scale parameter that helps us decide how much spread out the distribution is going to be. In other distributions, you have another parameter known as the location parameter. Usually this is a shift parameter that tells us where this distribution is either centered or where its lower bound is. In the case of a normal distribution, the mean is the location parameter. When you specify a mean, the normal distribution is going to be centered on that mean. This is not generally true that always the location parameter is the same as the mean. In most cases, this would not be the case. This is actually just specific to the normal distribution. But the point I'm trying to make is that the location parameter tells us where the distribution is centered. You can also talk of skewed distributions that are bounded on the lower end by some value. You can also define a shift parameter telling us that where this distribution is starting from. In other words, what is the lower bound of this distribution? So with these parameters, we can choose one particular distribution from a family of distributions. As an example, we can choose one particular normal distribution from the family of normal distributions. I hope the point of parameters is clear. Let's now talk about the light tail distributions. So remember, these are the distributions which belong to the world of mild randomness. And these are very commonly studied in statistic courses. We're going to cover some of them which are relevant to our field of study, which is network performance evaluation study. In a future session, we're going to talk of heavy tail distributions, which are distributions which belong to the world of wild randomness. But let's start with light tail distributions. Furthermore, you can also make a dichotomy that even in light tail distributions, you can talk of a discrete distribution and a continuous distribution. So this needs some explanation. So to illustrate this, consider a random experiment. A random experiment is an experiment the outcome of which is not known to you. So for different random experiments, the randomness can manifest itself in different ways. For example, the randomness may be in what possible outcomes could occur. And also, you might not be knowing the probability of those particular instances occurring. So usually this randomness is quantified by a probabilistic model, which is quantified by a probability mass function in the case of a discrete distribution, and a probability density function in the case of a continuous distribution. Let me make this clear. Initially, let's talk of discrete distributions. When we talk of a probability mass function, it tells us before the random experiment is conducted that what is the average case scenario that we would expect if we were to conduct this experiment a lot many times. This is the frequentist approach to probability. So in a probability mass function, you would have information about what outcomes could occur. So that is represented on the x-axis of the probability mass function. You can see one probability mass function on the slide now. So you see that the outcome could result in values of 0, 1, 2, 3 till 10. And then you need something more to define the randomness. You do not only need what outcomes are possible, but also what are the relative probabilities of those occurrences. So that is illustrated on the y-axis of this probability mass function, which tells us what is the probability of the outcome taking the exact value which is specified on the x-axis. For example, the probability of taking the exact value of 5 is 0.25. As you can see on the slide, you can also see for the other outcomes. So this is how we specify discrete distributions. Later on, we'll be seeing that when we talk of continuous distributions, it does not make sense to specify what exact outcome would occur. You can only talk of ranges of interval in which you can specify that the outcome may belong to this range, and you can then talk meaningfully about the probability of the outcome coming in that particular range. Because in continuous variables, continuum of values are possible, and because when we talk of a continuum of values, you have infinite values even between 0 and 1. Between any 2 points on the real line, you have a continuum of values. So for any one particular value, the probability of the continuous random variable taking that particular value is 0. So this is confusing to most people, but this should not be confusing, because we can remove this confusion by talking in terms of intervals, because you will never have some exact precise value as an outcome of a scientific experiment. And we've seen earlier that all measurements are wrong, and we've seen that how continuous variables require infinite precision. So what we have in continuous random variables is the probability that the outcome would be in certain range. And that is what we can talk about meaningfully when we talk of continuous distributions. So back now to discrete distributions. We've seen that randomness in such distribution is specified by a probability mass function. And now we are going to see some common discrete distributions. And we are going to see the probability mass function of each of them. So we are going to cover some simple distributions, like the uniform distribution, which tells us that the probability of all outcomes is equally probable. So you can see the probability mass function of a discrete uniform distribution on your screen now. You can see 6 possible outcomes, and the probability of taking each one of these outcomes is 1/6. A property of probability mass function is that if you add up the probability for all possible outcomes, it should be equal to 1. So this is the probability model that we commonly assume for rolling of a die. So let me make one point very clear here. When we talk of this probability mass function, this is an ideal mathematical model, and the physical die that we roll may or may not live up to it if we conduct a lot many experiments. In the short term, you would always find that there is some discrepancy between the actual outcomes that you empirically observe from rolling dice and from the ideal probability model that we have, because the probability model that we have is a mathematical model. And if you recall our discussion on mathematical models, you would remember that they are always approximate. They are approximations which are useful, but they probably will not be exactly manifested in practical terms. So we must always distinguish between data and the abstraction we use to represent the data. They are not the same. Let's now talk of another kind of a distribution. So the rolling of a die is an experiment in which you have some outcomes, and the probability of taking each one of those outcomes is equal. In many cases, in real life scenario, you have usually the case of either you make it or you do not make it. Either you get something or you do not get it. We can model such an experiment by a Bernoulli trial. A Bernoulli trial is a random experiment in which you can have 2 possible outcomes. You can call one outcome as a success and the other outcome as a failure. Success and failure should not be construed literally. Usually, when we specify that this event is going to occur with such a probability, that event can be replaced with a label which is success. In many cases, our intuition or our general idea about success may not match what is being defined as a success. So imagine saying that the probability that this person would die is this much. So that person may die or may not die. In this case, when we've defined the probability, the event associated with that probability is a success. So in such a case, the person dying would be a success, which helps us understand that this success and failure thing is just a label and it is not to be construed literally. So a Bernoulli trial is going to have 2 possible outcomes. So we say that one is a success, one is a failure, and because there are only 2 possible outcomes, we can specify the whole detail about the experiment by just specifying one probability, which is the probability of success. The probability of failure would only be 1 minus that probability, because there are 2 possible outcomes and the sum of the probabilities have to add up to 1. So a real experiment that you can model with a Bernoulli trial is the flipping of a coin. So when you flip a coin, it is going to come as a heads or a tails. There are no other possible outcomes if we ignore the possibility of the coin coming and standing on the edge, which is for practical purposes, it's not going to occur. So we only consider heads and tails. And in such a case, we can specify the probability of heads by some value p, and we can call the coming of heads as a success. As mentioned earlier, this specification of heads as success is fairly arbitrary. You can specify tails as a success, but then you would need to specify the probability of that. So if we want to specify the probability mass function of a Bernoulli trial, you would have two outcomes shown on the y-axis, and you would have probabilities of both of those outcomes. For one outcome, the outcome of success, you would have a probability of P, and for the failure, you would have the probability of 1 minus P, which is often shortened to Q. So Q is just 1 minus P. As an example of Bernoulli trials that are repeated, you can imagine flipping a coin 100 times. So we've drawn a figure that you can see on the bottom of your screen now. The tick mark, which is above the central line, represents a head, and the tick mark below the central line represents a tails. So you can see how things turn out if we conduct many of these Bernoulli trials. Many of the interesting distributions that we are going to study, especially of the discrete kind, are actually built on the basis of performing multiple independent Bernoulli trials. So the meaning of independence is that, okay, if you flip the coin now, it comes out as a heads. The coming of a heads does not influence what are the chances of the outcome on the next flip of the coin or on the next Bernoulli trial. So independence generally means that what has happened does not change the present or does not influence the future. So let's now talk of how we can use Bernoulli trials to solve some interesting questions. So one question that we may have is that if we were to conduct n number of Bernoulli trials, what is the probability of having exactly k number of successes? If we're interested in doing such a problem, the right distribution for us is the binomial distribution. So binomial is similar to Bernoulli in that you have two possible outcomes. Then we are interested that if we do many experiments, what is the probability of having exactly k number of successes? So let's see now at the formula for calculating the probability mass function. So you can see that on the slide now. The probability of the random variable taking the value k, or the probability of having k number of successes, is given by the formula here. So P is the probability of having a success. You raise that to the exponent of k, which is the number of successes you want. 1 minus P is the probability of failure, and n minus k is the number of failures you would have if you have k number of successes. So in that light, you can understand the formula. The binomial distribution has two parameters. The first one is a positive integer n, which tells us the number of Bernoulli trials. And we also have to specify P, which is the probability of having a success. So if we have these two parameters, we can calculate the distribution, which can give us the probability of having different number of successes. The mean for such a distribution is calculated to be NP, and the variance of such a distribution is calculated as NP multiplied by 1 minus P. Let's consider some examples of a binomial distribution. Every time you are conducting many trials, you can think of the sending of bits. Every bit is a trial in which the bit may be corrupted or may not be corrupted. So if you send, let's say, 100 bits packet, what is the probability that 5 of those bits were corrupted? What is the probability that 1 of those 100 bits was corrupted? So whenever you have two possible outcomes, you can use the binomial distribution. Other example is number of items in a batch which has a certain characteristic. This is having two possible outcomes because the item may have that characteristic or it may not have that characteristic. And because we're interested in the number of items, this would correspond to a binomial distribution. Let's now do an example to illustrate how the binomial distribution works in practice. So consider a LAN in which you have 10 stations. At any given time, a node can be active with a probability of 0.1. So we have n, which is 10. We have p, which is equal to 0.1. So now we can calculate the binomial distribution, which can help us answer many interesting questions. Questions like, what is the probability that exactly one station is active? What is the probability that exactly 5 stations are active? And what is the probability that all 10 stations are active? So using the formula that we just defined, we calculate the probabilities. So the thing that we see in the formula, in which you have n and k written in a bracket, so that is how many ways can you choose k items from a population of n items. So the formula for this is n factorial divided by k factorial multiplied it by n minus k factorial. So using this formula, we calculate the probability of having exactly one station active as 0.38. You can see the calculation on the screen now. What is the probability of having exactly 5 stations active? If we use the formula for calculating for value of k is equal to 5, we find that it is equal to 1.49 into 10 raised to minus 3. And what is the probability of having 10 stations active at the same time? We see that that is a very small probability. You can also see the graph which is showing the probabilities for various values of stations being active. You would see that it is actually very rare to find more than one station being active at the same time. And we can use this for the design of our network. You can see that the probability of having 10 stations active at the same time is so small that it would not be very efficient to design a network in which you expect 10 stations to be active at the same time. Obviously, you would need to have more provisions of bandwidth and of networking equipment. We can make do with a lot less equipment, because in packet switch networks, the probability of having multiple nodes being active at the same time, it's actually quite negligible, as demonstrated in this example. So this example actually illustrates one of the principles on which packet switching is based, which is that you usually do not expect a lot number of hosts to be active at the same time. We can also talk of a distribution which is similar to binomial but still different. It is known as the negative binomial distribution. In such a distribution, we are interested in calculating the number of failures we would expect before so many successes. Imagine that you want to have 5 number of successes. Now you want to calculate, before you see 5 number of successes, how many failures do you expect? And for each one of the failure counts, you would have a probability. And that is the negative binomial distribution. You can see on your screen now a PMF which corresponds to a negative binomial distribution, in which the target number of successes as defined by n is equal to 5, and the probability of having a success is 0.5. So you expect, as you can see in the PMF, it is going to take you around 3 to 4 failures before you have 5 successes. The probability of having 0 failures before 5 successes is actually quite small, less than 0.04. And you have a whole distribution, as can be seen on the screen. A special case of the negative binomial distribution is when we are interested not only in calculating for n number of successes, but only for one number of success. The question then is that if you want to do many Bernoulli trials, how many failures do you expect to see before the first success? As an example, assume that a fair coin is being tossed. You want to estimate the number of failures that you would have before your first success. So the exact question is, what is the probability that a head would be seen in a single toss, in 2 tosses, or 3 tosses. So for that, we use the formula, which is the probability of seeing the first success in X number of trials is equal to P multiplied by 1 minus P raised to X minus 1. Because if we expect the first success in X number of trials, X minus 1 number of times you would expect to fail. That's the reason we have the exponent of X minus 1. When we use this formula for calculating the probabilities of having a head in 1 toss, 2 toss, and 3 toss, it is calculated as the probability of getting a head in a single toss is equal to 0.5 raised to 0 into 0.5, in which case you don't have a failure. So the probability is 0.5. If you want to get heads on the second trial, then you would have 1 failure and 1 success. In that case, your probability would be 0.25. If you are interested in finding out the probability of getting a heads on the third trial, you would have 2 failures and then a success, giving you a probability of 0.125. I must make a very important point here, that the geometric distribution is the only discrete distribution which is memoryless, which means that whatever has happened in the past does not change the probability of future occurrences. So, as an example, imagine that you are tossing a coin and it has come up as 10 tails in a succession. But when you are actually interested in now calculating for the future, the history does not matter. In that sense, we can say that this distribution is memoryless. The memory of past occurrences does not affect the probabilities that we are calculating for future occurrences. And geometric distribution is the only distribution which has this property, only discrete distribution. Let's consider now a similar example, but now in the domain of networking. So consider a link having a loss probability of 10%. A packet is retransmitted until correctly received. What is the probability that it would be transmitted exactly 1 time, exactly 2 times, exactly 3 times? So to answer this, if a packet has to be transmitted only 1 time, there would be no failure. If it has to be transmitted 2 times, there has to be a single failure. If it has to be transmitted 3 times, there has to be 2 failures followed by the successful delivery. So this is actually very similar to the example that we just did. So let's now solve this question. We calculate the probability of the packet being transmitted and delivered on the first trial as 0.9. The probability that would take 2 transmissions for the packet to get through is actually just 0.09. The probability that you would require 2 retransmissions plus the original transmission is 0.009. Now if we see this example, this illustrates another basic fundamental of packet switching, in which you specify that if a packet is not delivered, you retransmit the packet. We can see by understanding the geometric distribution that it actually makes sense, because the chances of having many number of retransmissions is very slim. I must make an additional observation here, and that is that geometric distribution, and before that binomial distribution, assumes independent trials. In many cases, in practical terms, it may not be ensured. So because of that, it may be that network conditions are such and which persist for a long time, which is going to influence many trials. So the thing which caused the retransmission for the first trial may actually cause the retransmission for some subsequent trials as well. In such a case, the independence assumption is violated, and because of that, the results that we get from the simplistic geometric distribution may be misleading. Okay, let's now talk of the Poisson distribution, which is a very important distribution. and it is used a lot traditionally in network performance evaluation studies. It can be thought of as a counting distribution in which you are interested in how many number of events that are random and happen at a constant rate, how many of these events occur in some interval of time. So we can think of the Poisson distribution as the limiting form of the binomial distribution. There are many examples of Poisson distribution, and this is actually quite commonly used in telephone networks, the kinds of networks we had before data networks. So for the typical PSTN networks, Poisson distribution works very well, and in fact it worked very well for the queuing theory, which was developed for the telephone networks. We would see that Poisson distribution does not work as well for data networks because of some peculiar properties of data networks that we would study in a future session when we talk of extreme variation. So some examples of Poisson distribution are: how many calls do we expect to receive in a single hour? If we assume that the calls are going to come with some constant rate, then this is an example of a Poisson distribution. The number of typing errors performed, this is also a Poisson distribution. The number of cars that pass a toll booth in a minute. So ignoring the possibility of cyclostationary characteristics that we have because of time of day, assuming that we're given a rate which is going to remain constant, then using the Poisson distribution we can calculate probability for different amount of numbers of cars passing the toll booth. A classic case in which Poisson distribution was applied was the number of Prussian cavalry officers killed by mule kicks. And this illustrates one important point, and that is one cavalry officer dying from a mule kick does not influence other cavalry officers. So this illustrates that Poisson distribution assumes independence, and it assumes constant arrival rates. So in fact this happened over a period of 4 or 5 years, in which the cavalry officers, some years none of the officers died. In some other years you had one officer dying. Some other years you had, some particularly bad year, you had up to 5 or 6 cavalry officers dying. So you do know the average number that you expect, but you also know that you would have some variation around this. So when you have such a scenario, you can actually model using the Poisson distribution. The formula of the Poisson distribution is shown on the screen now. And one very important characteristic of the Poisson distribution is that its variance and its mean are the same. So it has a mean of lambda, which just specifies the number of events that you would expect in some interval of time. And the variance is also lambda. This illustrates that you do not expect wild randomness. You expect some randomness, but that randomness is not very wild. Okay, let's do an example of Poisson distribution, and imagine that you are doing some trial, the probability of success in which is 1 in a million. But also assume that you are conducting this trial a million number of times. What is the probability of having at least one success? Another question. A large meteorite hits Earth on average of 1 time per every 1,000 years. What is the probability that there will be no meteorite hits in the next millennium? In both these questions, we are given an average rate, and the interval is different. For the first one, you have 1 in a million chance. In the other one, you have 1 in a 1,000-year chance. But the average rate, the lambda value is 1. So it is worth emphasizing that Poisson distribution only has a single parameter. It is similar to binomial distribution, but the binomial distribution, if you recall, had 2 parameters, n and p. Poisson distribution only has a single parameter. In both these cases, parameter has a value of 1. What we are interested in is, in both cases, finding that 0 events happen. So this is then very easy to solve using the Poisson formula, which can be seen on the screen now. And if you plug in the value of 1 for lambda and the value of I is equal to 0 into this formula, you would see that the term lambda raised to I over I factorial vanishes, because that is equal to 1. And we are left with e raised to minus 1, which is equal to 0.37. So every time your average rate or your lambda is 1 and you are interested in finding the probability of having 0 events, you would get this value. And now let us generalize to the cases where you have different rates. So you can imagine the Poisson distribution to be the limiting form of the binomial distribution, in which the value of n is very large and the value of probability is very small. And then you can use the product of n and p to calculate the lambda. And you would see that for a binomial distribution calculated with the value of n is equal to 25 and p is equal to 0.04, it is practically identical to the Poisson distribution calculated for lambda is equal to np is equal to 1. So you can see that they are almost identical. So this is one way in which we can understand the Poisson distribution. So we considered the case in which the number of calls that you receive in 1 hour, we said that such a call can be thought of as being taken from a Poisson distribution. So we can imagine the number of people in your city. There are millions of people, so n is very large. The probability that they will call you is very small, but you can actually, by taking the product of np, you can find a rate at which you expect the events to arrive. In this case, the number of calls to arrive. Let us now change topics and talk about continuous distributions. We've talked earlier that when we talk of a continuous distribution, the random variable can take a whole range of values, a continuum range of values. Therefore, it does not make sense for us to say that the random variable is going to take this exact value. What we say instead for continuous distribution is that what is the probability of the continuous random variable being in a certain range. And the standard way for defining the continuous distribution is in the form of the probability density function and the cumulative distribution function. You can see both on the screen now. You can see the PDF, which is the probability density function, actually tells us the probability of the continuous random variable being in a certain range. But we must remember that in a probability density function, the y-axis does not represent the probability. It only represents the probability density. We have to integrate this density over an interval to find out the probability. To emphasize this, I've chosen a special curve in which you can see that the y-axis value or the density values are actually more than 1. This would never be the case when you have probabilities on the y-axis. So when we were talking of discrete distributions, the probabilities never exceeded 1. In fact, the probability of all outcomes actually summed to 1. In such a case, you see that for a normal distribution in which the mean is 0 and sigma value is 1 over 4 pi, you would see that some densities are actually more than 1. How do we then translate this into the form of probabilities? One standard way is to use cumulative distribution functions which tell us what is the probability of having a value equal to some value or less than that. So you can see a graph of that on the screen now. I'll conclude this lecture by talking of a single continuous distribution which we've already covered, the normal distribution. And we'll be covering more continuous distributions in in the next session. So for a normal distribution, it has two parameters. It takes a parameter value for the mean value and also a parameter value for the standard deviation. Alternatively, you can also specify the variance. A normal distribution is a very important distribution. It arises in many practical settings because of the central limit theorem. The central limit theorem tells us that when we are summing or we are taking the average of many independent random variables that have finite variance, we expect to have a normal distribution. My emphasis on finite variance is important because in many cases the central limit theorem would not produce a normal distribution because the random variables are coming from a population with infinite variance, and we would see some distributions that have infinite variance. So the formula of the density function is shown. We've also covered before the empirical rule, which is a very important rule which tells us what is the probability of having a value close to the mean. We said that within plus minus a single standard deviation, we expect to have 68% of the values. Within plus minus 2 sigma, we expect 95. And within plus minus 3 sigma, we in fact expect to find practically all of the observations, nearly 99.7% of the observation. This helps us, typify the kind of mild randomness. You see that most of the observations are very close to the central value. We would see that that is not always the case in network performance evaluation studies. So I'll see you next time when we talk more of continuous distributions. Assalamu alaikum.